this video is on calculating equilibrium constants, and we're working on this piece of paper, which doesn't really look like notes at all. It's more a problem solving. So, okay, so we've learned what Kc and Kp are. We've learned how to write them, how to write an expression for them, but we have not had a discussion yet in how do we calculate the value of Kc or Kp. So that's what this is on. And the first two problems, and you'll notice the heading says calculating K from equilibrium data. And so we have to keep in mind that Kc and Kp are equilibrium constants, and they have to be calculated with data from a reaction mixture at equilibrium. And that's super important. So the first problem says that we have a mixture of hydrogen and nitrogen, and it's allowed to obtain equilibrium. Let's see, it was analyzed and found to contain, and they give you some pressures. Okay, from this data, calculate Kp. All right, so we want to calculate Kp for this reaction. Okay, so, all right, so my first situation here is I should probably write a reaction, okay? And so my reactants, of course, are hydrogen and nitrogen, and we know that according to this problem, I make ammonia. These are all gases. Of course, I need to balance it. So, and 3. Okay, so there's my reaction. It's always a really good place to start. Anytime I have a problem, I need to write the reaction. So now they're asking me to calculate Kp. So a really good next step would be to write the Kp expression for this reaction. And we know that Kp is in terms of pressure. So it's the partial pressure of the products over the reactants raised to their coefficients. So this would be the partial pressure of NH3, that value squared because of the 2, over the partial pressure of H2 cubed, times the partial pressure of N2 to the first power. And so now I can calculate a value for this, or I can determine Kp if I know these 3 partial pressures, and it becomes a very simple problem. So I do in fact know those partial pressures. If you look at that second sentence, it says that the equilibrium mixture was analyzed and found to contain 7.38 atms of H2. So 7.38 atm of H2, and that value is going to be cubed. Now, I did reference before that Kp and Kc are actually unitless, so I'm going to leave my units off. It's the only time you're ever going to hear me say that. They're actually unitless numbers. Okay, so 2.46 atm of N2, so 2.46 atm of N2, and 0.166 of the ammonia. So 0.166, don't forget to square it, of the ammonia. All I have to do now is mathematically evaluate this with a calculator. And that's it. I have determined my value of Kp. It's quite a simple idea. So if you crunch that out on the calculator, I got 2.79 times 10 to the negative 5th as my value of Kp. If you didn't get that, make sure that you have cubed and squared your numbers, but otherwise you should obtain that value. Okay, and that's all there is to calculating a value for Kp. It's quite a simple idea. Okay, so let's do a second problem. And as always, if you want to try this one, you're welcome to. You can always pause this video. So the second one says, an aqueous solution of acetic acid is found to have the following equilibrium concentrations. Calculate Kc for the ionization of acetic acid. So in this case, they gave me the reaction, which is kind of nice. I don't have to write it on my own. And they're asking me to calculate Kc in this case. So remember, Kc is concentration. So always a good idea to write the expression. So concentration of the products divided by the concentration of my one reactant in this case. And everything's a 1, so I have no exponents. And again, in the second line of this problem, they give me those equilibrium concentrations. So I just have to plug those numbers in. Okay, so they tell me that the acetic acid is 1.65 times 10 to the negative 2, and they tell me that both the H plus and the acetate have the same concentration. And again, that's not a 1, sorry. Again, half this battle is just working your calculator. So if you input these correctly on your calculator, I got a value of Kc of 1.79 times 10 to the negative 5th for this reaction. Okay, so that's how you calculate Kp and Kc. Writing the expression and then plugging in the value. So it's pretty simple. But of course, this is going to get harder. And here's where it gets harder. So you notice your heading now says calculating K from initial and equilibrium concentrations. And so this is slightly different. So it says a closed system initially containing some H2 and some I2 is allowed to reach equilibrium. Analysis of that equilibrium mixture shows that you have a concentration of HI of 1.87 times 10 to the negative 3rd molar. Calculate Kc. Okay, so again, they give me the equation. And in this case, they're asking me to write, a Kc. I forgot. Okay, so again, I always start with my expression. So let me, just because I know what I'm, hold on, let me just move this over. There's a reason for that. You're going to see why in just a second. You're going to want to leave yourself room underneath this equation. Okay, so I'm going to go over here to write my Kc value. So products over reactants, of course. So HI over H2 times I2. Okay, and so you might be saying, what's the big deal? I have information on all three of these. I just plug it in and I'm done. But there's a big situation, and it is that these concentrations must be the equilibrium concentrations, okay? They cannot be initial concentrations. Now, initial means, at time 0, okay, at the very beginning of a reaction. And the beginning of a reaction, of course, is not at equilibrium. So, because Kc and Kp, for that matter, are equilibrium expressions, the only values that can go into those expressions are values at equilibrium. So if you notice, the first sentence says a closed system initially containing this much H2 and this much I2. Okay, those are initial numbers and they cannot go into this expression. I can't do it. So right now I don't know the equilibrium concentration of H2 and I2. I have to figure that out. However, I do know that the equilibrium concentration of HI is 1.87 times 10 to the negative 3. And I know that because the problem told me that at equilibrium, that's what its concentration was. But I don't know these two, okay? So you might say, well, then I can't solve this problem because I can't go any further. So this problem has to be solved in a slightly different manner, and it's called using an ice chart, okay? So the way an ice chart works is we kind of put a little grid underneath your reaction. And I'm going to label ice down the side. I should have left some more room. You can just write this, where I stands for initial, okay? C stands for change, and E stands for equilibrium. Okay, so we know the initial of these two, but we're interested in their equilibrium concentrations. Remember to plug it over here. So here's what we do. It's kind of like a grid, and I'm going to set up what I know. So I know this problem said initially I had 1 times 10 to the negative 3rd molar H2. And I dropped some sig figs, I know, but I can't fit them all in here. And I had 2 times 10 to the negative 3 molar I2. Okay. Now, if this is initially at time 0, that means this reaction hasn't started yet. And if this reaction hasn't started yet, I have 0 product. Okay, now they didn't come out and tell me that, but that's something that we're now learning. That initially, if I only have reactants at time 0, I have no product. Okay, so now, I do know one other piece of information, and that is that at equilibrium, the concentration of HI is 1.87 times 10 to the negative third molar. How do I know that? The problem told me that. Okay, they came out and told me that value. So, actually, this is kind of like a big math problem, okay? So what I do is we're looking for how do these concentrations change over time, okay? Well, if you think about this, the only way that I could have gotten from a concentration of 0 up to a concentration of 1.87 times 10 to the negative third is if I added, okay, or if my concentration increased by 1.87 times 10 to the negative third, because it's like a math problem. 0 plus this has to give me this, okay? So this is the change. The change of this is that it increased by this much. So if my product is increasing, then my reactants have to decrease. So these two are going to decrease by some amount. And all I have to do is figure out how much that is. And this line, the change line, is directly related to the stoichiometry of the reaction. So this number is representing the 2, which means now I want to find these numbers, which are represented by the 1. So of course I'm going to take this number and divide it by 2. And that's going to give me 9.35 times 10 to the negative 4th molar. 9.35 times 10 to the negative 4th molar. So what that means is that both H2 and I2's concentration decreases by this much during the reaction before it reaches equilibrium. So again, it's like a big math problem. To find this number, I take this minus this, and I will get this. And then this minus this will give me the equilibrium concentration. So once you do that, I got 6.5 times 10 to the negative 5th. And 1.065 times 10 to the negative 3rd. And then remember, like, why were we doing this, right? What was the whole point of this? Is to take these equilibrium values and plug them in to Kc. Right? Now, I already had this number plugged in because I knew it was the equilibrium. But now I know these two values. I know H2 and I know I2. And now, because I have all 3 values plugged in, I can numerically evaluate this expression for Kc. And once you do that, I got 50.5. Okay, so I have now successfully solved the Kc for this expression, or for this reaction, when I had not only equilibrium data, but initial data, and I was forced to use something called an ice chart. So ice charts are very prominent in the equilibrium chapter. We're going to see a lot of them in this chapter. So if you flip over, there's one more problem, and it's going to be another ice chart. You're welcome to try this one if you'd like, if you want to pause, but I will go ahead and put it up here. So gives me a reaction. And they asked me to solve for Kp. So over here, I'm going to write my Kp expression, okay? Products over reactants, so partial pressure of SO2 squared, don't forget your square, times partial pressure of O2 divided by partial pressure of SO3 squared. Okay, and again, if I can come up with these 3 numbers, then I'll be good to go. So, sulfur dioxide decomposes at high temperatures based on this reaction. Initially, okay, as soon as you see that word, we're going to need an ice chart. So, I for initial, C for change, E for equilibrium. Just a heads up so that you won't be surprised if this ever happens to you later. There are some college professors who call these rice charts, R for reaction, which I guess makes sense, but I don't do that. But if you ever hear somebody talking about a rice chart, that's what it is. Okay, so now let's see what we know. It says initially the vessel is charged. That means the SO3 is added. So SO3 at a partial pressure of 0.5 atmospheres. Now that's initial. So SO3 is 0.5 initially. Okay, so I put it in the initial column under the SO3. All right, what else do I know? At equilibrium, the SO3 partial pressure is 0.2. So at equilibrium, the SO3 partial pressure is 0.2. Calculate Kp. That's all they told me. Okay, so I'm going to treat this like a math problem. Now you might be able to figure out, of course, the only way for me to get from 0.5 to 0.2 is to subtract 0.3. Again, if my reactant is decreasing, then my products have to increase. So these are going to be pluses. Remember, this change line is the line that corresponds to the stoichiometry. So the 0.3 corresponds to a 2, which means the 2 is also going to be a 0.3. But this is a 1, so it's going to be half. And then this might be where students get stuck. But you have to remember that initially, if I had some, and that's at time 0, if I had some SO3 in my container, then I have no product in my container. Not initially, not at time 0. So then 0 plus 0.3 is 0.3, and 0 plus 0.15 is 0.15. Here are my equilibrium partial pressures, and I'm going to take them and plug them in to my expression. So Kp is going to equal the partial pressure of SO2 squared, so 0.3 squared, times the partial pressure of O2 over the partial pressure of SO3 squared. And as long as you evaluate that correctly, which shouldn't be a big deal here because there's no scientific notation, I got 0.338 as my value of Kp. Okay, so all you have to keep in mind when you're solving for Kc and Kp are, if I am given all equilibrium data, then these problems are plug and chug problems, right? You pull the data, put it in to the expression, and you're done. But if you're given initial data, you have to use an ice chart to find that equilibrium data to then put into a Kc or Kp expression to solve.